Hello everyone. So we are in part 2 of the electrophilic substitution reaction. So this is one of the important uh, type of the reactions. Okay. So in the types of the reaction, electrophilic substitution reaction is going to give more weightage in terms of the examination. So I want to give little more stress on the electrophilic substitution reaction because many named reactions are there and many previous questions are also arising from this concept. Okay. So in the last class we discussed about the halogenation and nitration. Okay, based on that I have given the workouts. Okay, so we're going to begin with the workouts. Okay, and later on we'll be going to see some more examples and some more electrophilic substitution reactions which are very important for the examinations. Okay, so the first question, benzene in presence of chlorine with the Lewis acid. Okay, so it's a halogenation reaction. So electrophilic substitution reaction, chlorination is going to happen. Okay, so irrespective of Lewis acid, okay, whether it is FeBr3 or FeCl3, whatever may be, it will be going to happen with halogens only, but not, it depends on the Lewis acid. Okay, so what I mean is, so whatever the halogen that you are taking is going to be matter, but not the Lewis acid. Okay, so Lewis acid you can take FeCl3, FeBr3, whatever may be there you can take. Okay, so it's not going to change the type of halogen. Okay, so Lewis acid is just for the addition or supporting agent. Okay, so it's going to initiate the electrophile formation. Okay, so that's what the importance of the Lewis acid. Okay, so if it is bromine, it's going to brominate. Okay, result in bromobenzene. If it is bromine, it's going to brominate. Okay, so bromobenzene, even if it is FeCl3, even if it is FeBr3. Okay, so when it is benzene and after chlorination, it's going to give chlorobenzene. Okay, and next, if it is bromination, it's going to give bromine substitution, but chlorine is a weakly uh, so ortho para directing group, which is deactivating type, weak. Okay, so it's going to direct the ring into the ortho and para when it is bromine and chlorine combination. It may substitute at ortho position and may substitute at para position, but the thing is, when it is para product, if it is compared with the ortho product, okay, so ortho is going to have repulsion because both are with a lone base which is going to repulse. Okay, always ortho positions are steric crowded, which will be going to repulse each other. So comparatively para will be the major. Okay, comparatively para will be the major. Okay, so the final outcome will be para chloro bromobenzene. Okay, so this is what B. Okay, let's begin with benzene and bromination. It's going to give bromobenzene. Okay, again if it is for the chlorination, there may be all the halogens are ortho para directing group. So there may be an ortho position that is going to take place and para position that is going to take place for the substitution. Okay, but among ortho and para, ortho will be sterically crowded, so para will be major product. So again it's going to give this. Okay, so in both the ways the product will be the similar. Okay, in both the ways the product is one and the same. Okay, so that's why I given two combination resulting into B. Okay, so let's go with the question number 5. So the question number 5 is about two synthesis, the dichlorobromobenzene. Okay, so how to deal with this? So if I do chlorination first, okay, what's going to happen? It's going to do chlorobenzene. Okay, so again if I further chlorinate it, okay, further chlorinated, it will be going to give at para position. Okay, so because at ortho position, if two chlorines are there, it will be sterically crowded. So, but I need to make into para position. Okay, bromine into the para position, but not chlorine. So, in the second step, I need to see I need to take the bromo substitution. Okay, so it is going to give bromo and chloro. Okay, so let me rewrite once again so that it will be more clear. Okay, so if I take benzene, okay, so my intention is to make 1,2 dichloro bromobenzene, 4 bromobenzene. Okay, so this is what my intention or final product or my desired product. Okay, so if it is treated with initial chlorination, it is going to give chlorobenzene. Okay, if again I treated with the chlorination, so what's going to happen? So at ortho and the para positions, chlorine is going to substitute. So among these two, which is the major product? So para will be major because it is going to have steric crowding. Okay. So again, if I do for the bromination, so what's going to happen? So 1,4 dichloro system is there. So both are ortho-para directing groups. As the para positions of each is already filled. Okay, is already occupied. So bromination is going to happen at the ortho position of one of the chlorine because both the chlorines are one and the same. Okay, so this is going to give. But our desired product is this. So how to make it is, so you need to go with the bromination initially. So it's going to give para bromo chlorobenzene. Okay, because at ortho position. Okay, so here also I can write the other possibility. This is sterically crowded, so it will not be major product. This will be major product. Now if I go for chlorination, so it's going to give the 1,2 dichloro 4 bromobenzene. Okay, so this way you can get your desired product. Okay, so only thing is the sequence of the substitution must be changed. Okay, sequence of the substitution must be changed. Okay, so whenever you want to make the bromine position at para, okay, bromine position at para, okay, to the chlorine, okay, you must take care of this. Okay, so there is another possibility where you can make the same compound by the starting with, if I think why should I start with only chlorination, can I start with the bromination? Of course we can. So if this is the case, so bromine will be substituted. Okay, if this chlorinated, okay, so it's going to take up at a para position. Okay, so ortho will also be possible, but it is sterically crowded. Okay, if at all ortho is also formed. Okay, so okay, if at all ortho is also formed. Okay, so you can use both the products. Okay, and these two products, if I treat with the one more chlorination, so what's going to happen? So this is para substituted, so it will be directed towards the ortho. Okay, because ortho of the bromine is more effective because it is less deactivating type. So ortho effect of the R2 substitution. Our directing tendency of the bromine is more when compared to chlorine. Okay, so it's going to direct towards itself as R2 for this compound. Okay, and at the same time, this is going to already occupied with the ortho position, so it must be going to takes place at para position of the bromine. So both the products are going to give the same. Okay, so among all these ways, okay, whatever the ways we discuss, the best way is this one. Okay, so you need to identify the best way so that the wastage of product, when it is two products are forming, there will be of course the wastage. Okay, as I am considering it as a major product, it doesn't mean that the other product is not forming. Okay, so of course the other product is formed, which may be a 20%, let's say. Okay, so here is a loss of 20%. Okay, so among that, again if it is going to generate another isomer, there will be another 20% loss. Okay, so the most efficient way to synthesize this is initially bromination, then followed by the dichlorination. Okay, initial bromination followed by the dichlorination. Okay, so to write in a simple way, bromination first and then Cl2, FeCl3. You can also add two times or you can write twice. Okay, so if you don't want to write as two, write like this: Cl2, FeCl3. Okay, so this is the best way. Okay, so you will be asked in the examination, there may be questions like this. So what is the sequential addition of the reagents? Okay, so to give the best possibility of final product. Okay, so let's go back to this. Okay, so I hope you understand the logic. Okay, so now my intention is to prepare fluoro, fluoro, chroma. Okay, so this is my intention. Okay, so let me write aside. So it's just a engineering. Okay, so engineering the product based on your requirement. So take the benzene and treat with bromine. Okay, so what's going to happen? So bromobenzene is formed. Okay, and if I treat with again chlorination, it's going to take a better para of that. Okay, as it is a major product. Okay, so of course there is a minor product also. Okay, so you need to take the major product for further reaction. Okay, so if I again treat with the bromination. Okay, sorry, chlorination. So as bromine is more directing, so it will direct the incoming group to the ortho of that, so the final product can be achieved. Okay, so can we make any other alternates? So instead of bromine, if I take chlorination, so it's going to give chlorobenzene, and if I treat with the, so I don't need parachloro. Okay, so if I use chlorine once again, it's going to give parachloro dichloro system. Okay, as a major product. So this is not my requirement. I shouldn't go with this. Okay, so what should I go with? So I need to go with the bromine. Okay, so chloro and mono. Now if I treat with chlorine, so of course bromine will be the most directing. So R2 to this is going to be product. Okay, so the two ways, here two ways are possible. The first way, bromination and dichlorination. Okay, and the second way, chlorination and bromination and chlorination. Okay, so these are the two ways that you can achieve the desired product from the benzene. Okay, so let's concise and write. First option A is bromination and two times. Okay, second, chlorination followed by bromination followed by chlorination. Okay, so it's just thought process. Okay, so if you able to think directly and can able to write the product, that would be uh, very much good practice for your examination. Okay, so try to get habitated with the donating nature. Okay, directing nature. Okay, so that you can make the products very easily. So next workout. So this is about the nitration. Okay, so if it is a chlorobenzene and nitration mixture treatment, so what's going to happen? Nitro group is going to add. So as the chlorine is orthopara directing, so para nitro will be more stable because ortho nitro will be having steric repulsion. Okay, steric repulsion. So if it is naphthol, okay, sorry, naphthalene, so this is also going to nitrate. So NO2 group is going to add, okay, at alpha positions generally. Okay, so methyl group, it is also weak activating group. Okay, so going to direct ortho and para directing. Okay, so para nitrotoluene is going to form. Okay, so two chlorines are there. These two are ortho para directing. So according to this is the para position. According to this is the ortho position. Both can support here. Okay, so at that position only it's going to substitute. Okay, so you can't just write on your own. Okay, so you should see the logic. Okay, so why not at other positions? Okay, so this is ortho. Okay, this is ortho to this chlorine and para to this chlorine. So if I write that product also, it will be one and the same. Let's see. So here, so look at this. So nitro and chloro are side by side and nitro and chloro are anti or opposite. Okay, so both are one and the same. Okay, so why not the other positions? So if I take this will be the meta to the both the groups, which is not supportive because those two are ortho para directly. Okay, if this is there, this position is ortho to both. Okay, so it can support to the ortho, but the thing is they are much repulsive. Okay, so steric crowding will be maximum. So you need to see all the regions. Okay, so among that best suitable regio selective isomer. Okay, so that you need to take out. Okay, so the position difference. Okay, you need to find out the best position, best region, so that regio isomer which is most stable will be as a major product. Okay, next, so this is going to give mono substitution when it is anilinium ion. Sorry, when it is aniline in nitration mixture, it is going to give mono substituted product that is also meta. Why? Okay. So I expect the answer from you. Okay. So couldn't get much answers from you. Okay. So when you are perfect with the explanations and reason tackling, then your concepts will be much clear when compared to the just going with the previous questions and all this. Okay, so noting down the reaction will not make much uh, hands-on for you with the organic chemistry. You need to think the reasons and find out the best reason for the best products. Okay, so here the main reason and the product which is going to get as nitroaniline is, here we are treating with the acid mixture which is going to donate the H plus, because this is a Lewis acid which can abstract, this is a nucleophile, it can abstract the H plus to result the anilinium ion, so NH3 plus. So when it is NH2, it is strongly activating group which will direct to the ortho and para position. But when it is NH3 place, it is strong deactivating group which will direct to the meta. So now NO2 electrophile will enter and it will be going to take place at meta position only. After the reaction, when we pinch, acid will be removed as well as the H plus will also be removed. So resulting meta nitroaniline. Okay, so make a note of this. Okay, this is very important. So when you treat the aniline with the nitration mixture, it's going to give meta nitroaniline but not orthopara nitroaniline, because anilinium ion is going to generate in the presence of acids which can direct the incoming group to the meta position, so resulting into the meta nitroaniline. Okay, so why not with the phenol? Phenol is not the Lewis base. Okay, so it is not that much Lewis base. Okay, so it will not abstract the H plus from this. Okay, so it will be going to activate the ring and it is a strong activating group. So nitration is going to happen thrice. Okay, so it's going to give tri-substituted phenol. Okay, so 2,4,6 trinitrophenol, which is called as a picric acid. Okay, so when it is phenol treated with the nitration mixture, it's going to give picric acid, trinitrophenol. Okay, so to make it less substituted or to decrease the availability of the NO2 plus electrophile, we must use the dilute acids instead of the concentrated acids. Okay, so that mono substitution can take place. Okay, so when it is mono substitution, OH group is ortho and para directing group. Okay, so it can direct to the ortho, it can direct to the para. Okay, so among these two, so which will be major? So far we have studied the ortho will be having steric crowding and para will be having less steric crowding. But the thing is, whenever OH group and any hydrogen bonding groups are there, okay, whenever hydrogen bonding groups are there, then the ortho will be major because of the hydrogen bonding. Okay, so because of the hydrogen bonding, ortho group is there. So how to determine whether a group can go for the ortho and will result into the major, or whether to go at para and will result into the major product means? So you need to see first hydrogen bonding. Okay, find the hydrogen bonding. If it is hydrogen bonding, ortho is major. Okay, if not hydrogen bonding, then para is the major. Okay, so if it is hydrogen bonding, alpha is major. If it is not hydrogen bonding, para is the major. Okay. So hope you understand the reasons. Okay. Finding the reasons and able to give the reasons is the best way to improve your subject knowledge. Okay. Instead of just rewriting the reactions. Okay. So next, if it is pyridine. Okay. If it is pyridine, it is also going to give nitration. Okay, so here the question comes with whether to go for at the second position, third position, or fourth position. Okay, so to know that, it is what, it is a electrophilic substitution reaction. Okay, so where This is the pyridine. Okay. So at third position, okay, at third position, it will be going to result the electrophilic substitution reaction. Okay. At second position, it will be going to give nucleophilic substitution reactions. Okay, remember this. Okay. So nitration is going to happen at third position. Okay. But the thing is, pyridine will not react directly. Okay. So it is less reactive because of the intactness or less reactivity of the pyridine, okay, to the nitration mixture. Okay, for that we will use high temperature. Okay, so pyridine will not react directly, it requires high temperature. So at high temperature we are going to make it nitration. Okay, so this was the last class discussion. Okay, so far. So now it comes for the reactivity in the cyclic groups. Okay, so what I mean is, if I have pyrrole, okay, and pyridine, okay, so which is more reactive in electrophilic substitution reaction? So if any two molecules or four molecules are given and asked for the reactivity order, so what could be the explanation for that? How to deal with them? The thing is, it is electrophilic substitution reaction where benzene is going to act as a electron rich system. Okay, so what the benzene is having, it is electron density. Okay, it is having electron density. So whenever electron density is there, okay, so it's going to attract the it's going to attract the el electrophiles. Okay, so that reaction will be more, isn't it? So what you need to see is electron density. So reactivity in electrophilic substitution reaction directly proportional to the electron density. Okay, you can write this conclusion also. Okay, so whenever it is asking for the electrophilic substitution reactivity, you just need to see electron density. So in the last classes we have seen that when it is a benzene with donating group will be more reactive when compared to benzene with withdrawing group. Okay, this conclusion we derive. Okay, now the thing, a 5-membered and 6-membered groups are there. Okay, rings are there. So which is more reactive? Undoubtedly 5-membered rings are more reactive because we are comparing electron density. What is electron density? So let's say if it is having 5 atoms in this and this is having 6 atoms in this, isn't it? But the pi electrons that is having in this ring is 6, okay, and pi electrons it is having is 6, okay. So 2 from this and 2 from this, 2 from this. So this is 6 electrons per pi atoms. Okay, 6 electrons per pi atom. This is 6 electrons per 6 atoms. So this will be almost equal to the 1. This is greater than 1. Okay, that is 1.2 around. Okay, 1.2. So electron density 1.2 electrons per atom is in this 5-member ring. So 1 electron per atom in the 6-member ring. So which is more electron density? So which is having more electrons? So 5-membered will be having more electrons. Okay. So among 5-membered and 6-membered rings, 5-membered are more reactive. Okay. So this question has been asked in the HCU very very repeatedly. Okay, so based on the same concept, question may be different based on the same concept. It's been asked. Okay, many times. So 5-member rings more stable than compared to 6-member rings. Okay, so more reactive. So because more electron density. Okay, now let's compare the give the reactivity order in electrophilic substitution reaction of below. Okay, so here I am giving A as benzene, B as pyridine, okay, and C as pyridine with iron water, and D as pyridine. Okay, so try to give. I'm sorry, find out. So fatafat, try to give the order of the reactivity. So what could be the order? So here you need to see first ring size. So 5 members will be the most reactive because more electron density. So D is the highest. Okay. Among these, so it is carbon here, it is nitrogen here. Okay. So it is the only variable, not all you need to see. Okay. So try to compare first with these two. Okay. So other than this, okay, so everything is same. So in carbon and nitrogen, does carbon is more electronegative or nitrogen? So of course nitrogen is more electronegative. So if it is carbon is giving 1 electron, okay, so when nitrogen is there, it will not give 1 electron because it is more electronegative, so less than 1. So electron density on this will be less when compared to the benzene system. Okay, so benzene will be more reactive, okay, when compared to the pyridine. Okay, so in the pyridine with triene group. So whenever with triene group is there, it will be less reactive. So it will be C, then sorry, it will be B, then C. Okay, so in this way you need to see the reactivity. Okay, so this is about the reactivity. Okay, so here I want to give one more question. Okay, exactly similar to this. So which, let's write the order. Write the order of electrophilic substitution reaction in of following. So you've been given A benzene, B furan, and C furan, and D thiophan. Okay. So this is the question that is most repetitive from the heterocyclic chemistry as well as the electrophilic substitution reaction. Okay, you can also find in HCU papers. Okay, so very very important. Okay, so what do you think? So far I given the 5-member rings are more reactive when compared to 6. So A will be the least. Okay, because it is 6-member, these all are 5-member. Okay, So among these three, which will be more electron density having molecule? Okay. So how these are aromatic? These are aromatic because they are going to donate the lone pair. Okay. They are going to move their lone pair. Okay. So this is what having 2p orbital, and this is what having 2p orbital. This is having 3p orbital. Okay. So whenever five-member ring systems are there, and you need to compare the conjugation, okay, or compare the electron density, you need to see the orbitals, outermost orbital, because the if it is donating the lone pair, the receiving, okay, is going to done by the carbon, which is into the 2p, okay, into the 2p. So when it is 2p 2p, there won't be energy gap. So easy conjugation, easy overlapping. But when it's 2p 3p, there will be difficulty in the overlapping. Okay. So among these three, this is going to donate less. So when it is going to donate less, or when the two electrons are not involving in the conjugation efficiently, so the electron density around the ring, okay, so electron density around the ring will be less. So that's why the thiophene is going to be less electron efficient, okay, less electron efficient. So it will be going to react less when compared to other two. Okay. So this is what the concept between 2p and 3p. So we eliminated this one. Okay. Now these two are having same 2p and 2p. Okay. So if it is 2p and 2p, how to deal with this? Okay. So every time I used to mention only one thing in the comparison question. You need to see the variables. Okay. So what are the variables you are able to see? So this all is same. The two molecules. So the variable is oxygen. The variable is nitrogen. So among oxygen and nitrogen, which is the more electron donating in nature, or which is having less, more electron negative? So nitrogen is less electronegative when compared to oxygen. So when it is oxygen is more electronegative, it will donate less when compared to nitrogen. So which will be donating more will be going to have more electron density and will be going to react more. So this will be more when compared to this. Okay. So a small question might be smaller, but it needs a lot of reasons so that you will make it's accurate. Okay. So accuracy is our main concept, but not the shortening the questions and shortening the subject. Okay. So this is about the reactivity order. Okay. So you need to focus more on this. Okay, because this is very repetitive question. Okay. So let's focus more. Okay. So next reaction is sulfonation. Okay, which is also a electrophilic substitution reaction. Okay. So what is sulfonation? Addition of SO3 group is called sulfonation. Okay. So for sulfonation, we are going to take the benzene as a starting material and 2 moles of H2SO4 as a sulfonating agent. Okay. Sulfonating agent. Okay. So why 2 moles? So if I use H2SO4 plus H2SO4, so one of the H2SO4 releases H plus and one will be going to take up that. Okay. So which is released the H2SO4 will become HSO4 minus. Okay. And the other molecule which is going to take the H place. Okay. So what's going to happen? This becomes H2O plus. So will be eliminated. Okay. And at the same time this also eliminated. Okay. So resulting into the S43. Okay. So this is double one, this is double one, this is double. So S43 is going to form here. Okay. Along with the H2O molecule. Okay. So this can be write as H3O plus. Okay. Because this is minus, this is plus. Okay. So here the electrophile is, so far we have discussed the halogenation where halogen is the electrophile, okay, and nitration NO2 plus is the electrophile. But in sulfonation it's not the same as the other two. Here the electrophile is SO3, okay, SO3. So sulfur trioxide, which is a neutral electrophile, okay, this is neutral electrophile. So this is the only one which will go through the neutral electrophile, okay. So what happens? So SO3 is generated if you treat with the 2 moles of H2SO4, okay. So let me write the SO3 and let me elaborate the benzene. It is going to attack and it's going to become like this, okay. So it become O minus and this will be the place, okay. So in this the sigma complex formation and everything is same, okay. After that the H place can move here which will be attacked by this, okay. So it's not mandatory that only this hydrogen is going to take up by this oxide ion. There can be available H place in the reaction mixture itself from the H2SO4, okay, that can also be abstracted, okay. So resulting what? So benzene with SO3H, okay. So benzene sulfonic acid, okay. So what happened? When benzene is treated with 2 moles of sulfuric acid, it will be sulfonated, okay, sulfonated, okay. So this is what sulfonic acid reaction, okay. So during the electrophilic substitution reaction, I have given that sulfonation is a thermodynamic reaction but not kinetic reaction, okay. So it is in under the temperature conditions, okay. So thermodynamic reaction, okay. So whenever thermodynamic reaction electrophile is there, so here the isotopic effect will be more. So if I replace hydrogen with the deuterium, the bond breakage will be difficult. So it will become slow. Okay, reaction will become slow. So when the speed is altered by the isotopic substitution, then it is said to be isotopic effect. So in sulfonic acid or sulfonations only isotopic effect is present. Okay. So not in other electrophilic substitution reaction. Okay. So this is one of the important points. Okay. This is also previous question. Okay. So mostly I used to repeat this is previous question, this is previous question. So does every question is going to arise in the previous examination? Of course, every question is been in the previous examinations. Okay, so they are going to repeatedly ask different important concepts. Okay, so which is going to include in your notes. Okay, so do follow the notes so that you can cover more and more previous questions. Okay, and as well as do practice the previous questions so you can easily tackle the upcoming examinations. Okay, so whatever may be your goal, like IIT JAM or Central University examinations. Okay, so you must need to refer the previous questions of that examination. Otherwise, it won't be possible to solve that questions at the time of examination. Okay, so next, if it is pyridine, okay, sorry, pyrrole, it requires the sulfuric acid along with the pyridine as a supporting agent, so that it will be sulfonated. Okay, so for 5 members rings, electrophile will attach at second position. For 6 member heterocyclic rings, electrophilic substitution will be at third position. Okay, So for this, it requires for pyrrole sulfonation is going to happen in the presence of pyridine, which decreases the acidity of H2SO4. Okay, so that it will enhance the formation of sulfur trioxide. Okay, so it will be going to react faster and resulting into the sulfonated product. Otherwise, it will not form. Okay, but why not pyridine? If I use, does it going to sulfonate on its own? It will not happen because the pyridine sulfonation is going to happen at the high temperatures. Okay, so it requires minimum 150 degrees centigrade. Okay, so high temperatures are required. Okay, so pyridine is used as a supporting agent which decreases the acidity of the sulfuric acids. Okay, so one more important point regarding the sulfonation. Okay, if it is naphthalene, okay, if it is naphthalene treated with the sulfuric acid, there will be two condition. If it is low temperature or if it is kinetic product, it will be going to take up at alpha position. This is to the bridged ring or fused carbon. If it is directly attached, it will be alpha and the other will be beta. Okay, so at alpha position it will be sulfonated. Okay, if it is high temperature, okay, high temperature, then it will be substituted at beta position. Okay, this is also important for your examinations. Okay, so this is what sulfonation. Okay, so on naphthalene, so if it is low temperature, alpha sulfonated. Okay, if it is high temperature, beta sulfonated. Okay, so this is about the sulfonation. Okay, so next important is Gutterman Koch formylation. Gutterman Koch formylation. Okay, so it can be compared with Gutterman aldehyde synthesis. Okay, so Gutterman Koch formylation is on the benzene to result the formylation. What is formylation? Addition of farmer group. Okay, so this is what farmer group. So okay, so benzene to benzaldehyde. Okay, so this is also benzene to benzaldehyde. So the similarity is same. Okay, so starting material and the products have similarity. Okay, so both are same. Okay, so what could be the difference between these two? Only thing is reagent. It will be going to happen with the coach KO. So it will be going to happen with the CO carbon monoxide along with the HCl. Okay, this is going to happen with the HCl. Okay, and HCl along with the ZnCl. Okay, zinc chloride. Okay, so when a carbon monoxide is treated with the HCl, it's going to give formyl chloride. Okay, so HCl added to this, so this is called formyl. Okay, acid halide. Okay, so formyl chloride. Okay, so when this is treated, okay, so HCl treated with the HCl. So Cl is minus, H is plus. So in this, do the carbon is more less electronegative or nitrogen? So nitrogen is more electronegative, carbon is less electronegative. So bond pair will move towards this, and this is an electron deficient electrophilic center. So it will be going to attack on this So it becomes N minus. So H plus will be abstracted. So this is what. Okay. So this is called iminium chloride. Okay. So iminium chloride. Once this is treated with the ZnCl2, okay, so it's going to release the it will abstract. This is Lewis acid. It will abstract the halogens. Okay. So resulting into the carbocation. This is called iminium carbocation. Okay, iminium carbocation. Okay, so when this is treated with the Lewis acid, AlCl2. Okay, so AlCl2. So again, it's going to abstract the halogen. So what is going to happen? HC double bond O plus. This is called formyl carbocation. Okay. So you can also call if it is R acyl carbocation. If it is hydrogen, you need to say formyl carbocation. Okay. So as it is an electrophilic substitution reaction, carbocations are generated. So electrophiles. So benzene is going to attack onto the electrophiles and will be replacing. So this is plus. So after abstracting that, it becomes 5 on mode is okay. So C double bond O H, and this is what positive. Okay. So electrophilic addition reaction, sigma complex will form. Okay. Try to write the mechanism completely. So H plus is eliminated as the electrophile, resulting into what? Benzaldehyde. Okay. In this case, same electrophile is formed. So benzene is going to attack onto the electrophile. So positive charge will generate here, double bond. Okay. Okay. So always I used to say when imine is broken, okay. So H2 will be this side, O will be this side. When it is hydrolyzed, it's going to give carbonyl. Okay. So it is reversed to the carbonyl and amine addition. Okay. So condensation reaction that is going to happen between the carbonyl and nitrogen. Okay. Will be reversed when it is hydrolyzed. Okay. So it's going to give. So let's hold the positive charge. C double bond OH, and this if it is release of H plus. Okay. So resulting will be benzaldehyde. Okay. So with two different reagents, we are going to synthesize benzaldehyde from the benzene. Okay. So if we use HCN along with the Lewis acid in the acidic medium, then it is considered to be Gutterman aldehyde synthesis. Okay. When the same benzaldehyde synthesis from the benzene using carbon monoxide in presence of the AlCl3 in acidic medium, then it is post formylation. So both are given by the Gutterman only. Okay. So to remember this KO CH. So when it is KO is there, it will be having CO. Okay. So when it is aldehyde, it will be other reagent HCl. Okay. You can also make your own reagent system or your own techniques to remember this. Okay. So try to solve the questions for today. Okay. Phenol. It is treated with HCN along with HCl and ZnCl2. Okay. So what could be the major product? Okay. Okay. Pyrrole. You can write the workouts also in the same notes. Don't use the other notes because these are also running examples for your reactions. Okay. So include in the same note. Okay. So try to make your own notes readily every day. Okay. So if this is there in terms of BF3, here it is a Lewis acid. Okay, so what could be the product, right? And which is major. Okay, you need to write major product only. So the third one, same if it is treated with HCl in terms of HCl and using ZnCl. So major, and this if it is treated with CH3Cl along with the HCl, ZnCl, what could be the product? So that's all for today. So tomorrow we'll be going to discuss some more questions. Okay, and tomorrow we're going to finish the electrophilic substitution reaction and we're going to start nucleophilic substitution reaction, which is also very important. Okay, so